Hello, and welcome to the podcast, Schools of Revolutionary Science, Unified Theories of Physics. I am Daniel Ovalle, a current Science, Technology, and Society senior at the New Jersey Institute of Technology, and I'll be your host through this podcast. In the following analysis, we will inspect the process and development of theoretical physicists' search for a unified theory connecting quantum mechanics and general relativity, and the struggled search for the Higgs Boson particle, or God particle, using the Large Hadron Collider, or LHC. Before delving into the specifics of the LHC, an understanding of what questions physicists hope to answer through unifying these theories must be made. Let us first, however, establish a foundation in the two unifying theories of physics, quantum mechanics and general relativity. General relativity describes the geometry of our physical space. In Albert Einstein's 1922 book, The Meaning of Relativity, general relativity is described as the processes of physics that explains gravitation and how this force behaves. General relativity is especially useful in describing the behavior of largest scale bodies of the universe, such as stars and galaxies. General relativity, though, cannot explain forces in the smallest scale of existence. For that, science has developed quantum mechanics. Quantum mechanics is a field of physics which describes the three fundamental forces other than gravity. They are electromagnetism, strong nuclear force, and weak nuclear force. The only practically visible of the three is electromagnetism, which manifests itself in the electronic devices we use every day. Quantum mechanics differs from general relativity in the scope of forces that they respectively explain. Quantum mechanics works on the small scale, and general relativity works everywhere else. The purpose of current theoretical physics is to unify the two established theories of physics, quantum mechanics and general relativity, into a simple and all-encompassing form. In the September 27, 1905 article, Does the Inertia of a Body Depend Upon Its Energy Content?, Albert Einstein begins the work on unifying the quantum mechanics and general relativity theories by challenging the problems with classical mechanics as he seeks to explain the actions and relations of matter and energy in the simplest terms possible. These postulations in unifying quantum mechanics and general relativity culminated in the equation E equals mc squared, equating energy to mass and explaining the phenomenon of radiation energy emanating from matter. This equation was the only one required by Stephen Hawking's 1988 book, A Brief History of Time, in which Hawking explains an understanding of theoretical physics to the layman and also explains the superstring theory. Let us now look at the more current works in the studies of theoretical physics, though it seems unfair to denounce the work of Einstein and Hawking as dated while their work continues to generate the field forward. Tyler Cabot is a features editor for Esquire and has written pieces for the Atlantic and Washington Monthly. In his December 2006 Esquire magazine article, The Theory of Everything, Cabot describes the questions being asked by the minds of theoretical physics. According to Cabot, these physicists fall into two schools of thought, whose physical representation is manifested in two very different theoretical physics think tanks. One of these is the Institute for Advanced Study, or IAS, in Princeton, New Jersey. Famous as Albert Einstein's stomping grounds during his postulations on unified theories, and described by Cabot as the Ivy League of physics think tanks. From IAS, Cabot focuses on two physicists, the father of M-theory, Edward Witten, and the connector of black holes and quarks, Juan Macadena. While their areas of study seem quite different, they are unified in their structured approach to their issues. The other school of thought is the Perimeter Institute for Theoretical Physics, or PI, in Waterloo, Canada. Founded in 2000 by Mike Lazaridis, who is also the founder of Research in Motion, the maker of the BlackBerry, PI relies on a more fluid, free model to the researchers' schedules. Cabot specifically accounts the words of one such researcher, Laurent Vidal, a faculty member in quantum gravity and particle theory, who states, "You don't let it go. You don't stop. And sometimes, if you don't need to, you don't stop at all for 2 or 3 days in a row. But that's the fun part. When you're on track, and when you know something's out there, there are no rules. You need intuition to make a connection. The key for me is not to let go, to continue until I reach it, and there's always a way. And so, the members of PI are awarded many freedoms, moving from field to field and choosing their work hours. These freedoms then allow physicists to question the overall purpose of physics research in general. One such researcher, outlined by Cabot's article, is Lee Smolin, a one-string theorist turned loop quantum gravity theorist. The environment of PI allowed him to make the switch and question physics in general without threatening his livelihood. In Smolin's 2006 book, The Trouble with Physics, as John Harnett states in the review of the book for the Mathematical Intelligencer, Smolin attempts to explain the complexities of string theory to the public. But possibly more important is that in the book he questions the social pressures of the scientific research community, which, in Smolin's opinion, has propped up string theory despite glaring problems based on the assumed consistency of space and time. He then argues for interest in the current field of loop quantum gravity in which, as Cabot states, space, time, and even people are all formed from the same network of interconnected loops and nodes, which take on electrical charges when twisted. There's obviously major dissension between the different unifying theories and theorists. This dissension is compounded as means of obtaining evidence for one theory above another theory. Luckily, there is hope for real data in the not-too-distant future. Near Geneva, between 50 and 175 miles under the Swiss and French border, there lies a 27-kilometer wide circle, which may provide humans with the means to finally understand how all processes in the universe work. This is the Large Hadron Collider, or LHC, the latest efforts in huge particle colliders by CERN, the European Organization for Nuclear Research, who have had such a collider in planning since the 1980s. In Cabot's The Theory of Everything, he uses the LHC and the nervousness connected to it to bookend his inspections of the new romantic heroes of theoretical physics community. The LHC is designed to smash tiny particles of matter into each other using superconductor magnets to accelerate the particles to speeds nearing the speed of light, and is situated with the state-of-the-art data collection sensors which will observe the remnants of these collisions. In these experiments, theoretical physicists hope to gain definitive knowledge towards their field, and hope to observe phenomena such as the creation of tiny black holes or proof of the Higgs Boson particle or God particle. This particle is theorized to be the subunit of matter that awards all matter its mass. Unfortunately, though, the collider has been plagued by misfortune and has yet to complete a substantial number of reliable, important tests. After the latest, particles have been placed back into the LHC, according to CERN's Twitter page on October 26, 2009. Time will tell what discoveries are made as the researchers at CERN continue to tackle the continued problems. Well, thanks for listening to this podcast. Once again, I'm Daniel Ovalle. Look out for more podcasts from NJIT and NJIT students.